Good day, I'm Norman Wahlberger. Last time we introduced polynumbers, which are simpler versions of polynomials. Today we're going to talk about elementary arithmetic with these new objects. So I remind you the basic setup. We have the positive numbers 0, 1, 2, 3, and so on. And we said last time that a positive polynumber is an object which is created from a list of positive numbers written vertically with a bracket on top. That defines a new type of mathematical object, polynum plus. So it's like a positive number, but a positive polynumber. And I should say perhaps that this list is by definition non-empty, so there's got to be at least one entry in the list. And we'll say that if we order the elements P0, P1 down to Pk, then we'll say that this is the 0th coefficient, this is the first coefficient, and so on. So P sub I is the ith coefficient of P, and we're starting our indexing at 0 up at the top. And a little bit of abbreviated notation. Instead of writing this big list like this, we'll just write P equals P sub I. And we'll say that the degree of our polynumber is the largest index k, which has a non-zero coefficient. So we read down to the last fellow, which is non-zero. And the degree is the index. The zero polynumber, its degree is not defined, all right? So we will not talk about the degree of the zero polynumber. And I remind you of our convention for equality, that if you have a polynumber, you're allowed to add zeros at the bottom of it, and we say it has not changed. You can add zeros, or if necessary, subtract zeros. We can say that another way by saying that Pi can be considered to be 0 if the index I happens to be bigger than the degree. Okay, here's a definition of addition of two polynumbers. So here's one polynumber P, and here's another polynumber Q. So the coefficients are Pi here and Qi. Then we say that the sum is the polynumber R, whose ith coefficient is just the sum of the ith coefficients of P and Q. So for example, to add this polynumber with this one, we add the 0th coefficients, we add the 1 coefficients, the 2 coefficients, and the 3 coefficients. The 3 coefficient here is 0. So we're adding 0 to this 7. Another example, even simpler, that the polynumber 11 plus the polynumber 7 equals the polynumber 18. So we see that ordinary addition of numbers is kind of contained in this arithmetic of polynumbers just by looking at very simple ones of degree 0. And then it's not too hard to see that addition satisfies the commutative law, and it satisfies the associative law, and that if you add the 0 polynumber to any polynumber P, you get back P. Addition is easy. Multiplication is a little bit less easy. Okay, so here's the definition of multiplication of two polynumbers, which I hope you figured out from the examples I gave you last time. So here's one polynumber P and another polynumber Q. Then their product, P times Q, is the new polynumber R, whose ith coefficient is given by this expression. Let's have a close look at it. It's very important. It's the sum over all positive numbers k and l that add up to I. The sum over all those KLs, P sub k times Q sub l. So we're multiplying one coefficient from P times one coefficient times Q, and we have to choose the indices so that they add up to our given index I. And we add up all of those possible products over all such possible indices. So here's a very simple example. 3 times 2 equals 6. So here the 0th coefficient times the 0th coefficient here is the 0th coefficient here. Let's have a look over here. Polynumber 4,1 times the polynumber 3,7. To find the 0th coefficient of the result, we look at the 0th coefficient here times the 0th coefficient here. because 0 plus 0 is the only way of getting two numbers adding up to 0. We get 12. When we look at the first coefficient, so this would be I equals 1, then we have to look at all pairs of indices that add up to 1. So we could take 0, 1, they add up to 1, or 1, 0. And the corresponding products are 4 times 7 plus 1 times 3. We add them together, we get 28 plus 3 is 31. How about when I is equal to 2? Well, what coefficients add up to 2? What about 1 plus 1? That equals 2. Okay, so we have to take that product, 1 times 7. So here's a little bit more complicated one. 102 times 314. The 0th coefficient is the product of these two. The first coefficient is this times this plus this times this. This coefficient is this times this plus this times this plus this times this. The two coefficients have to add up to 2. And this one here, that's when I equals 3, we can get that by taking this times this, which is 0 here, plus this times this, that's also 0, plus 2 times 1, that's 2, plus 0. So we get a 2. And we also get a coefficient from I equals 4, because that's the result when k is 2 and L equals 2. This times this equals 8. That's multiplication of two polynumbers. And it satisfies some various laws. Commutative law, associative law, a distributive law with respect to addition. And note that I'm using the usual convention that multiplication takes priority over addition. So you have to multiply these two first, and you multiply these two, and then you add these two resulting. And also, p times the poly number 1 is just p. So in fact, you are very familiar with this kind of multiplication, but in a slightly different form. Let's illustrate that by looking at this particular example. So convince yourself that the poly number 3, 1 times the poly number 2, 3 is 6, 11, 3. 2 times 3, 6. 9 plus 2 is 11. And 0 plus 3 plus 0 is 3. Now that computation is reflected in the ordinary way in which we multiply the Hindu Arabic numbers 13 times 32. 13, 32. Because one way of, a very naive way of thinking about how this product works is to take, well, this is 2 times 3, which is 6. That's the ones result. How many tens do we get when we multiply? Well, there's 2 times this 10, so that's 2 tens there, and there's also 3 times this 3 tens, so that's another 9 tens. So altogether there are 11 tens that result. And how many hundreds are there? Well, we get hundreds by taking this 10 and multiplying it by these 3 tens. 1 times 3 is 3 100ths. So the product of these two numbers is 6 ones, 11 tens, and 3 hundreds. Now we know that we don't usually leave it in this form because we don't like to have numbers bigger than 9 in any one spot. So we would convert this 11 tens into 1 10 and 10 hundreds, giving us altogether 416. But if we left it at this stage here, then we would have exactly what we got when we multiply the corresponding poly numbers. So polynumber multiplication is really not much different from the way you multiply two numbers ordinarily in the Hindu-Arabic system. And of course, this multiplication reflects the usual multiplication of two polynomials. If we take the polynomial 3 plus x and the polynomial 2 plus 3x, and we multiply them together using the distributive law, we get 6. The number of x's is 2 plus 9, that's 11. And the number of x squareds is 1 times 3, which is 3. So that's the point of it all. We are mimicking what happens with polynomials, but we're doing so in a way that does not involve x's. Next time we're going to look at arithmetic with polynumbers in even more detail. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.